So good evening students. Today we will see the basic concepts of wedge friction with an example. It's a piece of wood or metal, usually of a triangular or trapezoidal shape in cross section, used for lifting loads or for slight adjustment in tightening keys for shafts. So the wedge can be analyzed by either equations of equilibrium of forces or Lami's theorem. Anyway, we will see with an example. So the given problem is a block overlaying a 10-degree wedge on a horizontal floor and leaning against a vertical wall, and weighing 150 kg is to be raised by applying a horizontal force to the wedge. Assuming coefficient of friction between all the surfaces in contact to be 0.3, determine the minimum horizontal force to be applied to raise the block. So here you can see wedge is there and then block is there. Wedge is having an angle of 10 degree. The block is having a weight of 150 kg. So when we are applying a horizontal force P, because the wedge will move towards right, so the block will go up. Because block is in contact with the surface and also wedge is in contact with the floor. So when we are applying a force P, obviously the block will move up. So the condition is very clear, that is we have to determine the minimum horizontal force. So the block is in equilibrium condition only, otherwise it is about to slide. So we can take the condition as equilibrium condition and then we can substitute the equilibrium equations. Otherwise we can use Lami's theorem. It depends on the number of forces acting on the system. So first we will write the given details in the problem. The first one is weight of the block. So 150 kg. So here I am multiplying with 10. So it is 1500 Newton. Generally we will go with 9.81. Both are correct. Next one is the coefficient of friction for all the surfaces are given as 0.3. And very important thing is here we are calculating the angle of friction. So in the later part I will explain why we are calculating the angle of friction in this problem. So angle of friction, we know the formula, phi is equal to tan inverse of mu. So from that phi we can calculate, that is 16.69 for the given problem. So mu is given as 0.3, so we got pi is equal to 16.69 degree. The next step is we are drawing the free body diagram of wedge and block. So first we will see wedge. So we are representing wedge as ABC. And the given problem is the wedge is having an angle of 10 degree and we have applied a horizontal force. This particular minimum horizontal force we have to calculate. The condition is we are applying towards right. So obviously we will have a frictional resistance with respect to the surface AC towards left. So this force is frictional force 1 I am taking. And we know very well that because the wedge is in contact with the floor, so it will have a normal reaction, that is N1 we are taking. So the frictional force and the normal force we can replace with the single resultant, that is R1. So R1 is equal to root of N1 square plus F1 square. So next one we are moving to the surface BC. So because the minimum horizontal force is acting towards right, so the frictional force will be towards up in the inclined plane or towards left in the inclined plane. So this frictional force we can mention it as F2. And the next component is normal reaction. That normal reaction will be perpendicular to the surface BC. So this is N2. So again, as I said in N1 and F1, this N2 and F2 we are going to replace with the single force, that is nothing but the resultant, that is R2. So now if you see the diagram, instead of representing F1, N1 and N2 and F2, we can write it as R1 and R2. For example, N1 and F1 can be replaced with the single force R1 and F2 and N2 will be replaced with the single force, that is resultant R2. If we are substituting like this, then total number of forces which are unknown will be equal to 3. So easily we can calculate the unknown forces. After that we can relate it with F2 or N2 to calculate the force values and normal reaction values. So once again I will repeat that F1 and N1 can be replaced with a single resultant force R1. Similarly, F2 and N2 can be replaced with a single force, that is resultant R2. So these things we are doing for solving the problem simple, because instead of 5 unknowns, if we are considering R1 or R2, the unknowns will be 3, that is P, R1 and R2. Now we are moving to the block. So the block will have a load of 1500 Newton. Because we are applying a force, minimum horizontal force towards right, the block will move up. Because of that, the frictional force will act towards down. So here I am taking this frictional force as F3. And similar to the wedge, here also the FG surface is in contact with the surface. So we will have a normal reaction, that is N3. So these two forces, that is normal reaction and frictional force, can be replaced with the single force, that is resultant R3. So F3 can be called as limiting friction also. Even F1 and F2 also is nothing but limiting friction. Now we will come to the surface DG. Before going to that, I want to recollect one more important point, that is, when two bodies are involved and both tends to move with respect to each other. So here it is wedge and block. These are two bodies. So when two bodies are involved and both tends to move with respect to each other, then the reactive forces F and N. So here I am talking about F2 and N2. So if you see the wedge F2 and N2, F2 is acting towards left with respect to the surface BC and N2 is acting towards down with respect to the surface BC. So according to the definition, when two bodies are involved and both tends to move with respect to each other, then the reactive forces F and N acting on the bodies are equal in magnitude but opposite in direction. So when we are considering the surface at D and G, so F2 will be acting towards with respect to the surface DG, and then the normal reaction N2 will act perpendicular to the surface DG, that is towards upward direction. So now these two forces F2 and N2 can be replaced with the single resultant force, that is R2. So now we are going to find out the minimum horizontal force with this free body diagram. So we know that in wedge we are going to consider only three forces, that is P, R1 and R2. Similarly, in block also we are going to consider only three forces, that is 1500 Newton and then R2 and then R3. Anyway, we will solve one by one. So the next step is free body diagram of a block. So we know that it is 1500 Newton, that is the weight of the block, and then the frictional force, and then the normal reaction, and then these two can be represented as a single component, that is resultant force. And here you know that it is frictional force F2 and then a normal reaction with respect to the surface N2, and then these two can be replaced with the single force, that is R2. So as I said earlier, we are going to consider only three forces. For better understanding, I am going to substitute 1500 Newton and R2 and R3 in a XY plane. For example, so this is your XY plane. So we know very well that 1500 will act towards down. So the R3 which is making an angle with respect to normal reaction is nothing but angle of friction. So angle of friction we already calculated. So the R3 which is making an angle with the horizontal is similar to the R3 which is making an angle with the N3. So this angle will be phi. So phi we already calculated, that is tan inverse of mu, that is equal to tan inverse of 0.3, that is 16.69 degree. So same thing we are writing here. The next one is we are having another resultant, that is R2. So here it is acting. So these two are not acting on the same line, it is different. So we have to calculate the angle of R2 with respect to the horizontal line. So this angle we are going to calculate now. So this angle is nothing but we have to calculate with respect to the normal reaction. But here the normal reaction and this horizontal is not same, that is N2 and the horizontal axis is not same. So we have to calculate with respect to the slope. This slope is having an angle of, that is wedge is having an angle of 10 degree. So if this is 10 degree, obviously this one also will be 10 degree. And with respect to this particular inclined plane, our normal reaction is having an angle of 90 degree. So when I am calculating the value of R2 with respect to horizontal, the value will be 90 minus 10 degree minus 16.69 degree. We will get 63.31 degree. Again, I will repeat how I got 63.31. So with respect to the inclined plane, our normal reaction is having an angle of 90 degree. So I want to calculate only the angle of R2 with respect to horizontal. So inclined plane is already having a 10 degree. So we have to subtract that value with 90 degree. So 90 minus 10 degree will come. And then if you see the diagram, R2 is having an angle of 5 with N2. That value also we have to subtract from 90. So 90 degree minus 10 degree minus 16.69 will give the angle of R2 with respect to horizontal. So why we are doing this is because we want to resolve the component with respect to the X and Y axis for calculating the unknown forces of R2 and R3. So slowly you draw and then draw the diagram, then you will understand much better. So now we have drawn the free body diagram. So now we are going for the next step, that is step 3 is equations of equilibrium. So now we are having only 3 forces, so we can go with Lami's theorem, otherwise resolution of forces. Here I am going with resolution of forces. So the first one, we know that summation of forces along horizontal is equal to 0. So we will assume that towards right is positive. The inclined resultant R3 will be converted into horizontal component and vertical component. So it will have R3 cos 16.69, that is horizontal component, it is acting towards left, and then R3 sin 16.69, that is vertical component. So these things we have already seen in the earlier problem from the first module onwards. So next one is we are having another inclined force, that is R2. So R2 will have again 2 components, that is one is horizontal component, another one is vertical component. So this one will become R2, that is horizontal component is R2 cos 63.31 degree. The R2 will have a vertical component, that is R2 sin 63.31 degree. So if you see R3 cos 16.69 is acting towards left, that is horizontal component, and then R2 cos 63.31 is acting towards right, that is horizontal component. So R3 cos 16.69 is acting towards left, so as per our assumption it will have a negative sign, and R2 cos 63.31 is acting towards right, so it will be positive. So we are not considering R2 sin 63.31 degree and R3 sin 16.69 because these two are acting in the vertical direction. So now we can write R2 cos 63.31 as positive minus R3 cos 16.69 degree is equal to 0. As per the equations of equilibrium, summation of horizontal forces or summation of forces along x direction is equal to 0. So from this we can write R3 is equal to 0.468 R2. So this one we can take it as equation 1. Now we are moving to the next equation, that is equation of equilibrium. For that again we are taking the free body diagram. So that the second equation we know very well, that is the summation of forces acting vertical is equal to 0. Otherwise the summation of forces acting along y direction is equal to 0. So we are taking that the forces which are acting towards up is positive. So now in this free body diagram, if you see that 1500 Newton is acting towards down and R2 sin 63.31 degree is acting up and R3 sin 16.69 degree is acting towards down. So based on these conditions, so we can write minus R3 sin 16.69 degree minus 1500 Newton and then plus R2 sin 63.31 degree is equal to 0. So from this we can substitute the value 16.69 and then 63.31 and then we can write the equation as minus 0.89 R3 and minus 0.29 R2 is equal to 1500 And we have already calculated, that is R3 is equal to 0.468 R2. So we can substitute in equation 2, so that we will get 1977 Newton. So we got one value of resultant. So once we got R2, we are having another relation based on the equation 1. R3 is equal to 0.468 R2. So we can substitute the value R2 here. That is 1977 Newton. So we will calculate R3 is equal to 925 Newton. So now we got the values of R2 and R3. So the remaining things left out in our problem is R1 and P. So anyway, we will take the other free body diagram and then we will try to solve that. So now we are going to the step 4, that is free body diagram of wedge. So here we are going to calculate only 3 forces, that is minimum horizontal force P, and then single resultant R1 and single resultant R2. So now, as like previous, so we are going to draw the XY plane. So now we know that we are having a minimum horizontal force and then we are having a single resultant R2. So this R2, we have already calculated the angle with respect to horizontal, that is nothing but, so 63.31 degree. So here I did not mention as phi because it is not the angle of friction. So only I have given a separate term theta. So next one, we are having R1. So now we have to calculate this particular angle. So we know very well that the angle between the normal reaction and the resultant is friction angle. So that value will be 16.69. So based on that, if you want to calculate this particular angle, that is the angle which is made by the R1 with respect to horizontal will be, so we know that N1 is acting towards up and R1 is making an angle of 16.69. And the entire region, it will give vertical and horizontal will give 90 degree. So that 90 minus 16.69 will give the angle between the horizontal line and the resultant R1. So the total angle is 90 degree. We know that very well. So the angle made between R1 and N1 is 16.69. So simply I have brought that 16.69 with respect to the vertical. So the remaining angle will be 90 minus 16.69, that is 73.31 degree. So now we calculated the relation of angle of R1 and R2 with respect to horizontal. Now we can go for the equilibrium equation to solve this problem. So free body diagram wedge, you know that. So same thing I am taking. So in step 5, we are going to substitute the first equation of equilibrium. That is summation of forces acting along horizontal axis, otherwise x-axis is equal to 0. So as like previous, towards right, we are assuming it as positive. So here if you see that the component P is acting towards right, so it will be positive. But we are having two inclined force, that is R1 and R2. So we have to calculate the horizontal component, otherwise X component and Y component for these two forces. So first we will see R2 cos 63.31 degree and then R2 sin 63.31 degree as a vertical component. So R2 cos 63.31 degree is the horizontal component of R2 and R2 sin 63.31 degree is the vertical component of R2. And we are having R1, it is having an angle of 73.31 degree with respect to the horizontal line. So R1 cos 73.31 degree will give the horizontal component of R1 and R1 sin 73.31 degree will give the vertical component of R1. So now we got all the horizontal and vertical components. So we are going to substitute P, it is acting towards right, so positive, and R2 cos 63.31 degree is acting towards left, so negative. R1 cos 73.31 degrees also acting towards left, so it is negative. So we can write the equation P minus R2 cos 63.31 minus R1 cos 73.31 is equal to 0. So from this we can rewrite the equation P is equal to 1977 cos 63.31 plus R1 cos 73.31 because we know that R2 is 1977 Newton. So now we are moving to the next equilibrium of equation. So again we are drawing the free body diagram of wedge. the summation of forces about y-axis is equal to 0, otherwise vertical is equal to 0. We are assuming that the forces which are acting towards up is positive. You can see that two forces are acting vertical. That is, one is R1 sine 73.31 degree that is acting towards up, and another one is R2 sine 63.31 degree that is acting towards down. So upward is positive. So R1 sine 73.31 degree will be positive, and R2 sine 63.31 degree will be negative. So we can write R1 sine 73.31 degree minus R2 sine 63.31 degree is equal to 0. We can rewrite the equation R1 sine 73.31 degree is equal to 1977 sine 63.31 degree, because we know R2 is equal to 1977 Newton. From this we can calculate R1. So the R1 value is 1846 Newton. So once we calculated R1, then we can calculate the value of P. So we know that P is equal to 1977 cos 63.31 degree plus R1 cos 73.31 degree. So if we substitute the value of R1 in this equation as 1846 Newton, so we get P is equal to 1431 Newton. So this is the minimum horizontal force required to raise the block using the wedge. So here I have changed the angle of the wedge, that is 25 degree, and the weight of the block is 2500 Newton. The coefficient of friction between all the contact surface is 0.4. So again I am asking you to determine the minimum horizontal force to be applied to raise the block. So solve it and then post your answers in the comment box. So if any queries, ping me or message me. All the best. Have a nice day. Thank you.